Hello students. In previous class we have studied about the self-induction. I hope that you all have understood what is self-induction. Let's revise. In self-induction there is production of induced EMF whenever there is change in the current in the coil. Same case is here, but here current change will be in one coil and induced EMF will be set up in another coil. So this is called mutual induction. Mutual induction. It is the phenomena of production of induced EMF in one coil due to change in the current in the neighboring coil. Means if we have two coils, this is one coil and this is second coil, and this coil is connected to a battery, a key and a rheostat. So by rheostat and battery and key we can control current, we can give varying current in this coil, in this solenoid. And this is secondary coil, this is called secondary coil, this is primary coil. This coil is connected to a galvanometer. When key is off, there is no current in this. As soon as key is turned on, current starts flowing in this coil. When current in the coil P varies, it changes magnetic field around it because it is a solenoid. Whenever there is a current, there is magnetic field production. So it changes magnetic field around it. If current is varying, then changing magnetic field is there. Hence, there will be change in magnetic flux linked with this one. So induced EMF, induced current will be produced in this coil. Let us imagine that at any instant magnetic flux linked with the secondary coil is proportional to the current in the primary coil, because it implies that current induced EMF in this coil is dependent on the current strength, variation of current strength in this coil. So we can write phi is proportional to I, or for short terms we can write phi S is proportional to IP. Phi S is proportional to IP, current in the primary. So we can write like this also, IP. But for self-induction it was only phi is proportional to I and phi is equal to Li. But here phi in secondary is proportional to current in the primary. So phi is equal to M into I. This M is called coefficient of mutual induction. If I is equal to 1, if I is 1, then phi is equal to M. Phi is equal to M. If any change in the current is set up, then induced EMF will be there. Then E is equal to minus d phi by dt. Now put the value of phi Mi here. Then take M outside. Then E is equal to minus di by dt. If di by dt is 1, then E is equal to minus M. In previous case, in self-induction also, we defined phi is equal to L as well as phi is equal to L di by dt. L di by dt. If current is 1, then coefficient of mutual inductance is equal to the flux. If rate of change of current is unity, then coefficient of mutual inductance will be equal to the induced EMF set up in the coil. So any change in the current I sets up an induced EMF in the secondary coil. So we can define mutual inductance in two ways. Number one, mutual inductance of two coils is equal to the magnetic flux linked with one coil when unit current passes through the other coil from this one. And second definition we can get from this one. Second definition is mutual inductance of two coils is the induced EMF set up in one coil when current in the neighboring coil changes at the unit rate. So this is important. Here two coils are there. Change in one coil and production of induced EMF, change of magnetic flux for the other coil. That is why it is called mutual. And if same phenomena happens in single coil, current change is there, induced EMF is there, magnetic flux is there, then it is self-induction. If in one coil there is current change, in another coil there is change in flux and induced EMF production, induced current production, then it is called mutual induction. SI unit, M is equal to E di by dt, unit of E is volt, di by dt is 1 ampere per second, so 1 volt second ampere inverse, its SI unit is Henry. Therefore, mutual inductance of two coils, now we can define 1 Henry from this side. The mutual inductance of two coils is said to be 1 Henry. It is 1 Henry if an induced EMF of 1 volt is set up. Induced EMF is set up when in one coil when the current in the neighboring coil changes at the rate of 1 ampere per second. So the mutual inductance of two coils is said to be 1 Henry if, this is very important, sometime it is asked in examination, define 1 Henry. So just to define from this formula, the coefficient of mutual inductance is 1 Henry, is said to be 1 Henry if an induced EMF of 1 volt is set up in one coil and the change of current is unity in another coil, in neighboring coil. So this is definition of 1 Henry. Now mutual inductance of two long solenoids. Here these are two solenoids, S1 is 1 and S2 is another solenoid. S1 is having current I1 and S2 is having current I2, and they are coaxial with S2 wound over S1. These are two coaxial solenoids, S1 and S2, with S2 wound over S1. Length of each solenoid length is same. R1 and R2 are radii of two solenoids. Because radius is different, so number of turns in the same length is different. So that is why R1, R2 radii of two solenoids, N1 and 2, number of turns in two solenoids. Let a time varying current I2, now we focus on this part. Time varying current I2 is passed through S2. A time varying current I2 is passed through S2. When this time varying current is passed, then there will be change in magnetic field around this, and this change in magnetic field around this will change the magnetic flux of this coil also, S1 also. That change is important for us to calculate mutual induction. So magnetic field setup will be, let a time varying current I2 is passed through S2. So magnetic field around that solenoid will be B2 mu naught Ni. Mu naught N, because it is number of turns are N2, so we can take N2, where N2 is number of turns per unit length. So magnetic flux linked with S1 will be phi 1 is equal to B2 area of 1 and number of turns of 1, B dot A. B dot A, and total flux will be multiplied by number of turns. So phi 1, this is magnetic flux linked with the coil S1. This is magnetic flux linked with the coil S1. So phi 1 is equal to B2 A N1. So these two equations are very important. Magnetic field produced around one and flux linked with other coil. So for flux we will take area of that coil, and for field we will take area current of primary coil, previous coil. So phi 1 is equal to mu naught B, value of B, mu naught Ni, mu naught N2 I2. Phi is equal to BA, this is A, total number of turns N1. So phi 1 is equal to mu naught N2 I2 A N1. So take I2 this side. All this is constant, and this constant is called coefficient of mutual inductance, M12, mutual induction of 1 because of 2 with respect to 2, because change in current is in 2 and induced EMF is in 1. So it is M12. M12 is equal to mu naught N1 N2 A by L. So in place of number of turns, we can take number of turns per unit length also. In that case we can have, and for this area we can have pi r square also. So for this expression we can have three forms depending upon our requirement. In numericals we can use this also, we can use this also, we can use this also. Here area is pi r square, here N1 is number of turns per unit length N1, this L length will be cancelled and one length will be go upside. So mutual inductance of two coil is property of their combination, because in this everything is of both the coils, number of turns. So mutual induction of two coils is property of their combination. It depends upon number of turns, product of number of turns. It depends upon area. It depends upon distance between two solenoids. If distance will be more, then magnetic flux sharing will be less, because as a solenoid moves from magnetic field, its effect decreases. So it is inversely proportional to the distance between two solenoids, and mutual inductance depends upon the relative orientation of the coils. Relative orientation of means coils may be like this also, they may be like this also. In this case maximum magnetic flux will be shared, will be linked. So M will be maximum, but here minimum. So this is minimum and here maximum. Mutual inductance depends upon the permeability of the core material. If we wound this material and over a soft iron core, then its permeability will increase. So M will also increase. So M depends upon the permeability. M depends upon the number of turns. M depends upon the area. M depends upon the relative distance, orientations and distance between the two solenoids. So all these factors are important from examination point of view. Sometimes questions may be asked, just derive this, and sometimes short questions can be asked from this type of relations, and 1 Henry, definition of 1 Henry can be asked. So in the next class we will discuss its numericals of mutual induction.